Okay, students, in the second video about thermal physics and thermal concepts, I want to talk about a very important concept called specific heat capacity. And again, if you're in chemistry or if you've taken chemistry recently, this should be pretty straightforward for you because it's a pretty standard topic that all chemistry students would study, okay? All right, it turns out that there is a relationship between mass and heat transfer, okay? So for example, if you have, the easiest way to think about it is if you have a big thing that's very hot, okay, it's going to generate a lot more heat, meaning you're going to feel more heat coming from it than if you have something made of the same substance but a very small size or very small mass at the same temperature. It's not going to radiate as much heat, right? Okay. This has actually huge implications in terms of life on Earth and the way things are in the universe. So for example, if you've ever gone hiking in the summertime high in the mountains in a snowfield, you may have noticed that you have these funky areas around a snowfield, around snow, where the snow is melted. This also occurs around trees in a forest, in a snowy forest. You ever wonder why the snow melts away from the rock? Okay. Also, have you ever noticed how, if you're in an airplane, you ever notice how clouds tend to form on a sunny day over the land before they form over the water, over the ocean? Okay, all right. So it turns out that both of these two pictures are explained by the same physics, the same phenomenon. That's what I'm going to talk about in this video, okay? The same similar physical properties, okay? Now, if you provide thermal energy to a body, its temperature goes up. If you take away thermal energy, the temperature goes down. So for the same amount of change in heat, the change in temperature can be different. Why and what does it depend on? Okay, I'll do a couple of demos in class. The answer is completely related to two things. Number one, the mass of the object and the material from which it's made, okay, the density and so forth. Unit masses of different substances contain actually different numbers of molecules. Density, lead is very dense. Lead is much more dense than, say, aluminum or plastic. Different types and or individual masses, and I want you to think about atomic structure there, okay? Now, this concept called specific heat capacity, in physics we give it the symbol little c, confusing because the speed of light is also called little c, but we'll never deal with the speed of light in a specific heat capacity context. We don't have to worry about that. It's defined as the amount of thermal energy needed to raise the temperature of 1 kilogram of a material by 1 Kelvin, or 1 degree Celsius, because the intervals are the same. The SI units of a specific heat capacity are therefore joules per kilogram per Kelvin. Okay, so if this is the case, then it must mean that C equals Q over M times delta T. Okay, because it's the amount of thermal energy needed to raise the temperature of 1 kilogram of a material by 1 Kelvin. So the units work out joule, kilogram, Kelvin. Okay, if I rearrange this, I get Q equals MC delta T, and this is the form of this equation that we more often use. Okay, the idea of heat capacity or thermal capacity, which is a capital C, that's just the quantity, the mass times the specific heat capacity. You see this sometimes in the IB. In this case, you have Q equals big C times delta T, but it's all the same physics. So now, the thermal capacity, as you can see, big C depends on the size of the object and what it's made of. Specific heat capacity depends only on what the object is made of, okay? And I'll do more examples of this in class. Very important slide right here. Okay, so some specific heat capacities of different substances. I told you that what the object is made of, besides its mass, has a big impact on how heat is transferred from it and into it. Okay, you can see there's a huge range here, right? Water has a very high specific heat capacity, and that's a super important thing. That actually helps explain why clouds form over the land before they form over the ocean, and why the snow melts away from trees and rocks, okay? Now, interesting differences. Why is there solid liquid difference, right? Okay, well, water has a very high C, okay? Now, let me explain to you a little more in detail, okay, why it is, why water is so important and how water explains these two pictures, okay? In the case of the clouds forming over the land, okay, you have sunlight shining on the land and the water, okay? Because water has a much higher specific heat capacity than land, which is made of rocks and buildings and trees and dirt and things like that, water has a higher specific heat capacity. the same amount of sunlight, the same amount of energy shining on these two things, the land will heat up much more quickly than the water does because land has a lower specific heat capacity. You can think of water as having the ability to absorb a lot of heat without raising its temperature or lowering its temperature. Okay? Clouds are formed when hot air rises off of land very quickly. Hot air rises and reaches the condensation point in the atmosphere and then condenses on small particles. So this is proof that the land heats up quicker than the water. Now in the case of the snow, okay, well, every day that goes by when the sun shines on the snowfield with this boulder, the rock heats up. They're both exposed to the same amount of solar energy, right? The sun is shining at the same rate on both the snowfield and the rock. The rock heats up more quickly. Therefore, the rock melts the snow around it because the snow doesn't heat up it doesn't change its temperature as much as the temperature of the rock, okay? So, just another way that water is a very curious, even though it's a very common substance on the surface of the earth, it's a very unique substance. It's used as a coolant in engines, hot water bottles, and so forth because of its high specific heat capacity, okay? Okay, all right. Try numbers 8 and 9 on your own using Q equals MC delta T. Okay, for example, 8, how much heat is needed to raise the temperature of 20 kg of water by what? 15 degrees Celsius. Q equals MC delta T, I get 1250 kilojoules. Example 9, I got 39 kilojoules. Okay, so very, very straightforward stuff. Remember, lead and water have different specific heat capacities. They're very, very different in their chemical makeup, all right? Okay, so the way that we measure specific heat capacities is actually pretty ingenious. We'll do this in class. We'll do a lab. And to understand how this process works, you need to understand the term calorimetry. And it's the process of calculating specific heat transfers and chemical reactions and physical changes of substance. So the way that we do it is this. Okay, we take a particular substance, say this unknown material right here. Okay, we put it in boiling water for a long time. Therefore, if we put it in boiling water for a long time, the temperature of that substance is going to be 100 degrees Celsius. Okay? Now, what we do is we then remove this substance very quickly and we place it in an insulated container with a known mass of water at a known temperature for a long time. What's going to happen? Two things. The water is going to heat up and the mass is going to cool down. Eventually they're going to be in thermal equilibrium. Okay? We take the final temperature of the water to determine the specific heat capacity of the substance, and hence we can identify specific heat. We can identify what the substance is by doing this. Okay? So obviously this process utilizes the conservation of energy. This device is called a calorimeter. This is also called the method of mixtures. In the IB, you sometimes see that term. Okay, why does it utilize the conservation of energy? Very important for you to understand. The heat lost by the unknown material is equal to the heat gained by the water, and by using Q equals MC delta T, we can ascertain what that mystery metal is, and we'll do this in class. Okay, we'll have you guys figure out what a mystery metal is. Because it utilizes conservation of energy, we have to make sure that the calorimeter is as perfectly insulated as possible. Okay, we're always going to lose heat to the surroundings, but if we're careful, and typically calorimeters are encased in a styrofoam sort of casing, if we're careful, we can get amazingly accurate results. Okay, so try this one on your own using what I talked about in the previous slide. This is the calorimetry problem. Go ahead and try this one on your own. What might the substance be made of? Okay, so I take 1 kg of a sample, place it in boiling water, 100 degrees Celsius, then I put it in 2 kilograms of water, and I'm given the initial temperature of the water and the final temperature of the water. What's the substance made of? Okay, well, by conservation of energy, the change in heat of the solid is the change in heat of the water. I get 382.5 joules per kilogram per Kelvin, so it's probably, consulting the previous table that I showed you of specific heat capacities, it's probably copper. All right, pretty cool. Isn't this ingenious? It actually works, okay? And one more example before we close this video. Try this one on your own. Same idea, calorimetry, okay? All right, it's a little more, maybe a little more complicated algebraically, okay? You have to do some sort of fancy algebra, nothing you guys can't handle, okay? I got about 26 degrees Celsius for the eventual temperature of the water. So you see the concepts here of specific heat capacity and how we measure them in calorimetry, pretty straightforward. Again, it all really rests on the foundation of the conservation of energy. okay, which of course is never actually literal in real life, because we always neglect the heat loss, okay, in our calculations. And you'll find that when you do a lab using heat using heat and temperature, that actually that will be a big deal, the amount of heat that's lost in the surroundings. So as an experimenter, you're going to have to figure out how to minimize that and how to deal with that in your calculations during a lab write-up.